Okay, in this question, we have the function f of x equals this, and we have four parts, and they're all related in some sense. We need first to find and classify the critical numbers of f. So let's do this first. A. We need to find the derivative of f, which is, here is f. The derivative, you use the power rule. The 5 comes down, and 3 times 5 is 15. And subtract 1 from 5, you get 4, minus 3 times 20 is 60, x to the power 2. So to get the critical numbers, you set this equal to 0. And so take now 15x squared as a common factor. You will have x squared minus 4, all of this equal to 0. And so we're almost done. Just this, you can write it as 15x squared into difference of two squares. So x minus 2 into x plus 2 equals 0. And now you can list all the zeros. So x equals 0, or x equal minus 2, or x equal plus 2. You can say, because if you want to take them in order, so this one gives me 0, then this one gives me 2, then this one gives me negative 2. So good. Those are the critical numbers. So we have 3 critical numbers. 1, 2, 3. These are the critical numbers. But it doesn't mean that they are for sure maximum or minimum. It can be that one of them is neither a maximum or a minimum. Among the critical numbers, you have the maximum and minimum, but also things that are neither maximum nor minimum. So, for example, if in a graph, this is a maximum, so the slope at the maximum point is 0. If you have a minimum, then the slope at it is 0. So fine, if the derivative is 0, so if it's a critical point, then it's a candidate for maximum minimum. But look at something like this, for example. If we have something like this, like this, I need to draw it correctly. Just wait. Here, yeah, like this from here, and then goes up. Okay, at this point, notice that if you do the tangent line, it will be a horizontal tangent. Okay, I can even make it better so that you see that it is really indeed the tangent, yeah. But notice this point is neither a maximum nor a minimum. So even though f prime at this point will be 0. So if this point here on the x-axis is c, then f prime at c is 0 because the slope of this line, remember the derivative is the slope, so the slope of this red line, which is the tangent line at the point c, f of c, the slope of this is 0 because it's horizontal. That's what we did. We set the slope equal to 0, and we found that at 3 points the slope is 0. But you can have 3 conditions. It could be that you have a minimum or a maximum, or you have something that's neither a minimum or a maximum. Here also f prime at c is 0 if this is c, and if this is already it's drawn here c, then also f prime at c is 0. So if f prime at c is 0, it does not mean that automatically it's minimum or maximum. It could be a situation like this. But if you have a minimum or a maximum, then definitely the derivative at them is 0, so they are critical numbers. Okay, I will take this out now. Just it's a quick review. Nice to have it when you're solving questions, that you remember quickly the material surrounding this. So 3 critical numbers. and classify them. They said find, that's fine, but now we want to classify them. So we will put the x-axis here, so 0, and we have -2, and we have +2. And so what we will do is take the formula for the derivatives. The easiest one is this here. For me, at least, it's easier than this one. This one has more stuff in it. This one is nice to identify the zeros, but this one is nice to work with when you are, remember, this is just f prime of x. Yeah, it's easier to work with this. So now, what I want to see is f prime of x, its sine of f prime of x, and in the bottom is the behavior of f. I will make you understand what I mean by these two. Yeah, so notice that we said at -2 the derivative is 0. At 0 it's 0, and at 2 is 0. All of them it's 0. See, when we put f prime equal 0, we got the 3 points. So this means that f prime is 0 at each one of those 3 points. Perfect. Now choose a point here. Let's say you chose -4 or -5 and substitute it in f prime. Substitute it here. So if you choose something less than -2, anything less than -2 here, choose anything and substitute it in the formula here, you'll get, I will do this, so -3 squared, it will be 9 minus 4 positive, so here this is going to be positive. Between -2 and 0, choose something here, -1 for example, so it will be 15 and then negative. And because this is an even function, it will be the same on the other side, minus then plus. I mean, it will be kind of a reflection. Not kind of, it will be a reflection. But if you don't understand why, then just take points here and check that it will do the same as what's written on top of them. And now look at how nice this is. If f prime, the derivative, is positive, we know that this means that the function is increasing. Increasing, this means. Negative is decreasing. Negative, decreasing. Positive, increasing. And immediately you can identify here increasing, then decreasing. So we have a maximum here when x is -2. And when x is 2, notice, decreasing then increasing after it. So at 2 we have a minimum. Okay, and at 0, notice that it's decreasing before 0 and decreasing after 0. So it's neither maximum nor minimum. And so this A is done. Now we go to part B. Okay, so for part B, it says find the intervals where the function is increasing or decreasing. We see it already. Increasing, it's on 2 intervals. So you can say in B, f is increasing on the intervals on from -infinity to -2, or you write union from 2 to infinity. Those where you have the pluses, that for f prime, so it means increasing for f. And f is decreasing on, and you can see it's decreasing here between -2 and 2, on the interval between -2 and 2. So this answers part B, and we can go to part C. Let's use this color for part C. We will use just blue. So now part C. So find inflection points of f. So for inflection points, we need f double prime of x. That's now part C. Okay, so f double prime of x equals, now where is f prime? Here. This is f prime of x. So take its derivative again. The 4 comes down, and 4 times 15 is 60. So it will be 60. Subtract 1 from 4, you get x cubed. Minus, now go back to the formula here. And 2 times 60 is 120. So minus 120. And subtract 1 from 2. So 2 to the power, x to the power 1. Okay, and so you can also take 60x as a common factor here, and inside you'll have x squared minus 2. Okay, and you set this equal to 0. So f double prime, you set it equal to 0 and check, because the inflection points will be among the points where f double prime is 0. So now, if you set it equal to 0, it will imply either x is 0 or x squared minus 2 is 0. But x squared minus 2 is 0 implies x squared is 2, which implies that the absolute value of x is radical 2. Or you can say, what I mean by this is plus or minus. You take plus or minus x equals radical 2, and so x is plus or minus radical 2. So you have x0, let's highlight 0 and plus minus radical 2. These are the places where the second derivative, f double prime, equals 0. So we are going to draw 0, negative radical 2, and radical 2. And the same thing here, you do the sign of f double prime here, and down is the behavior of f. Remember, I will just say this one more time, that f prime controls the behavior of f related to increasing, decreasing. So the monotonicity of f is controlled by f prime. You know, increasing and decreasing is controlled by f prime. That's why when f prime is positive, increasing, f is increasing. And when f prime is negative, then f is decreasing. The same thing here, the sign of f double prime. When f double prime is positive, then f will be not increasing, but it will be concave up. That's what it means for the second derivative to be positive. And if the sign is negative, then it will be concave down. So this is what we'll do now. Check. Here we know that f double prime was 0 at those 3 points. And now you just choose numbers here and check f double prime positive or negative. So let's choose something here. Choose something negative 10, for example. And if you put it here, you'll get negative. Yes, and then between minus negative radical, between negative radical 2 and 0, we can choose negative 1 is here. So put it in the formula, you'll get minus, and then 1 minus 2 is minus. Minus times minus is plus. Then here, if you choose 1, then 60 times 1, so positive times 1 minus 2, negative, so negative. Positive times negative is negative, and then something bigger than radical 2, 10 for example, it will be positive. Okay, perfect. So now what we will conclude from this is that when f double prime is negative, f will be concave down, and positive concave up, negative concave down, positive concave up. But remember, this is f double prime. F double prime is what controls concavity. And notice now, very nice, that all the 3 points at x equal negative 2 and 0 and radical 2, at x equal negative radical 2, 0 and radical 2, all of them are inflection points. Why? Because concave down, then up before radical 2. So the function changes concavity at negative radical 2. At 0 also, before 0 it's concave up, after 0 concave down. So the function changes concavity at 0, so 0 is an inflection point. And similarly, for radical 2, it changes concavity from concave down to concave up. Perfect. And so last one now is part D. Find the intervals where the function is concave up or down. That's very simple. So now we do part D. We'll do it here. So part D, you will say f is concave up on, and f is concave down on, and we write the intervals now. So the first one, concave up, we see here it's up and here. So between minus radical 2 and 0, it's concave up, union, and also from radical 2 and on to infinity. That is concave up in these places, and concave down in the other places, in minus infinity up to negative radical 2, or in here between 0 and radical 2. So 0, radical 2. And this finishes the entire question, but I want just to tell you one thing, is to see the graph. Let's see the graph. I'm going to graph this function so that you see that everything that we got about it is correct. 3x to the 5, so let's do it. 3x to the 5 minus 20. So I'll just write it, y equal 3x to the power 5 minus 20x cube, minus 20x to the power 3. Okay, and let's close it for now and see what the graph looks like first, and check that all what we found was correct. So notice there is a maximum here at the point negative 2, and the maximum value is 64. Here at 0, 0, there is no maximum or minimum, even though the tangent line is horizontal. And at the point 2, we have a local minimum, and the local minimum value is negative 64, as you can see. So this is for maximum and minimum, and you can see increasing, decreasing easily on the graph. This function is increasing up to negative 2, and then it starts decreasing until 2, and then increasing afterwards to infinity, from 2 to infinity. So that's nice. And now about the points of inflection and concavity. You see, as I'm walking here, it's concave down, it's still down, it's still down, until you reach approximately somewhere here. You see that it changes from down to up. And that is the minus radical 2 something. And then there is another point here, which is radical 2 something, where you can see it changes concavity from concave down to up in this region. So, and also, of course, 0 is an inflection point. Look, before 0, as you are coming, it's concave what? It's concave up here, on the left side of 0, concave up. On the right side of 0, look, concave down here. So 0 is also an inflection point. So you see, we saw 3 inflection points. The first inflection point was somewhere here, the minus radical 2, comma, the value of the function at minus radical 2. Then 0, 0 is an inflection point, and then radical 2, comma, its value will be also a third inflection point. Just like what we found here, that at negative radical 2 and 0 and radical 2, all are inflection points. Okay, and I will stop here.